Okay, today we'll be learning about lenses. Most of the lenses, when seen from the front, they look circular like this, as seen from the front. But if we cut a lens like this from the center, and then we see it from this side, we will see either a lens like this. Talking about simple lenses. Some are complex lenses. They can be like convex on one side, concave on the other. The side that comes outward is called convex side. The side which is caved inwards is called concave side. Some lenses are concave from both sides. Some lenses are convex from both sides. Some lenses are plane on one side and convex on one side, like this. Some are like this. Okay, so and one form can also be like this. But luckily, we don't have these kind of lenses. This is plane, plano-convex. This one is plane, concave, and this one is convexo concave. So we won't be discussing these. Yeah. So let's discuss these two. The one that is convex on both sides, known as double convex lens, and the other one is double concave lens because it is concave on both sides. For any lens, the center point, this point, is called optical center. And we also call it pole. Okay. This point C is center of curvature. In this drawing, you can see that this side is actually an arc. Is this an arc? If this one is an arc, it belongs to a circle. So circle will have a center. So if you want to draw this arc with perfection, you can put the needle of the compass over here at center of curvature and make this arc. Then you will have exact same replica of this um, side of mirror, this side of lens. But we cannot call it an arc. It will be a curve. Why it is a curve? Because not a curve. Actually, it will be a curvature because it is not a circle's part. It is of a sphere because it will be a surface. So actually, this side belongs to a sphere. The center of sphere is at C. So we call it center of curvature. The midpoint of center of curvature and optical center is called principal focus. This is principal focus. And we have a replica of principal focus and center of curvature on the other side, because I hope you can see that there is this arc as well. So this arc will have the center of circle on the right hand side. The arc on the left has center on the right. The arc on the right has center on the left. So there will be two centers, two focal points, and one optical center for length. The line that joins all these points, the line on which all these points exist, that is called principal axis. What do we call it? principal axis. Now, the same kind of points, they exist for double concave lens as well. Now, properties. For double convex lens, when light rays are coming parallel to the principal axis, arrows are very important. So you can decide that whether the light rays are coming towards the lens or they are going away from the lens. So look at the left side of the double convex lens. I'm talking about this one over here. So when light rays are coming parallel to the principal axis, after passing the lens, they bend and they all converge on point F on the other side. When light rays are coming parallel to the principal axis, on the diagram, I have labeled the number, label every ray with the number 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. The line 4 is actually the principal axis. 1, 2, 3, 4, 5, 6 are parallel to the principal axis at different distances above and below the line. So when light rays go parallel to the principal axis and they pass through the lens, they converge on one point known as the focal point or principal focus. This is why a double convex lens is also known as converging lens. A double convex lens is also known as converging lens. Look, these details are written over here. When light rays strike double convex lens parallel to the principal axis, they bend such that they all pass through same point, focal point on the other side. This is why a double convex lens is also known as a converging lens. Okay. When somebody says converging lens, it means they mean double convex lens. Now, when light ray is coming parallel to the principal axis for a double concave lens, the light spreads like this. So here's a note for this one. When light approaches a double concave lens. If you already have this PDF with you, you can write it over there. With light approaches a double concave lens, it diverges all rays spread away from focal point or principal focus. This is why a double concave lens is also known as diverging lens. Why diverging lens? Because it diverges, it spreads the light outward. So if light comes parallel to the principal axis for a double convex lens, it converges on one point, focal point. And if light ray go through a double concave lens, then light spreads out, but it again spreads out away from the focal point F. Like, listen, if you want to know that how much this light ray will bend away. Okay. How much this light ray is supposed to bend away? Answer is that if this is the point you're looking at, I'm talking about this point. So if you look at this point, what you do is you connect this point to the focal point over here. This is the focal point. So you make this light ray go away from the F in this direction. Okay, if you backtrack this line, the line with the question mark on it, if you backtrack it, you will come back to point F on the same side. So all these light rays are going away from F point. So F is important for both lenses, whether it is converging or diverging. Now, for both of the lenses, if light ray is striking its pole, by pole I mean the center point, the light ray will pass straight through, undeviated. On your PDF, if these arrows are missing, please put them over there. Okay. So light rays, if they strike the pole, they pass straight through. So this is what you have to remember. If light ray is coming parallel to the principal axis, and I'm talking about double convex lens only. So these are the two properties that you have to remember for double convex lens. The light ray that comes parallel to the principal axis should bend such that it passes through F on the other side. And if light ray is hitting the pole, it is supposed to pass straight through, undeviated at all. These two properties, they will help us to make uh, diagrams to find out the position and the characteristic of images. Okay. Look. Image can be real or virtual. Image can be real or virtual. What is meant by real image? An image that can be produced on a screen it is same for any point of view. So no need to show position of eye. Virtual image. An image that we can see but cannot produce on a screen. An image that we can see but cannot produce on a screen is known as virtual image. The size and position of such image depends on point of view. So on diagram, an eye is shown for point of view. So if you will be dealing with a virtual image, you must show an eye over there because a virtual image can change in size and position, and there's a possibility that you won't even see the image if you're not at the proper position. Okay, one example of such image is in a mirror. If there is a mirror in your room and two, three people are sitting at different points in the same room in front of the same mirror, they all will be looking at different part of the room because of their position of eye, because their point of view, because they are looking at that mirror from a different side, they will be seeing a different reflection. You cannot see a reflection that another person is seeing in the mirror unless you go and sit on that position, or you see from the same angle and in at the same position. So uh, image in mirror is a virtual image because it depends on point of view. But if there is a projector in a class, no matter where you sit, you will see the same image. Okay. So that is a real image because it is produced on a screen and it does not depend on point of view. It will be same for everybody in the room. The image is same, like uh, it doesn't matter where you look at it, you will see the same image. But that is not the story with um, image in a mirror. So real image and virtual image. Real image can be produced on a screen, and same for all point of views. Virtual image is something that we can see but cannot produce on a screen, and that image is known as virtual image. Okay. Now, how the diagrams are made? Simple diagram. Now, this is a double convex lens. Now, to make double convex lens like this again every time, it is very difficult. So, easier way to do that is we draw a line on both ends. We draw a triangle. Okay, so this means the same. This means a double convex lens. Isn't it simple? So this is how you can easily make this diagram. Now, if we have a double convex lens like this will be the principal axis. say this is F, this is 2F for C. Similarly, there will be F on this side and 2F on this side. Okay. So if we put an object over here, now we want to see where the image is formed. So what we will do, because we know that there are lots of rays coming out of the head. It is an illuminated object, and most of them will fall on the lens, but we don't know path of every line. But we know the path for the line that is coming parallel to the principal axis, because it will bend through F on the other side. And the light ray that will hit the pole, it will also bend straight, or it will pass straight. Sorry. So I know path of these two lines. So here we go. So this is how we can track down where the image should be formed. For this kind of image, like this is the position where the image of the head is formed. So there is the image of the head. And because the tail is already on the principal focus, so tail will be formed on the principal axis, sorry. So this is how the image will be seen. This is A point of image. So A point of object, this is A point of image. This is B. So this is B dash. Arrows are very important. So this is how we track down different positions of images. Okay, let's see. Let's start. This is the first case. I will recommend that you replicate it right now. Like you can make a lens in your notebook by a vertical line. Take 3 centimeter distance for F and another 3 centimeter for 2F. If you put an object way behind 2F and draw the line parallel to the principal axis, make it go through F, and then draw a line through optical center, you can find out the position of image. Okay. So after the class, you can find the different positions of images. Number one, for the first diagram, what we will do, we will put an object. Object means object can be a flame, it can be a torch, can be any illuminated object. So if we put it behind 2F and draw a line parallel to the principal axis, make it pass through F on the other side, and then draw a line through the optical center which passes straight through and through. The point where they both intersect, that is the position of the head of the image, and we get the image over there. And we can see this is an upside down image. We call it inverted. I can compare the size of image with the object. The image is comparatively smaller than image is smaller than the object. Number two, it is formed between F and 2F. It is smaller, it is inverted, it is formed between F and 2F. And we exactly know the position of this image. Just put a screen over there and we can see that image. There's no requirement of any eye on this diagram. So this image is also a real image. So this is what you need to remember or understand. The best is that you understand it, and if you don't, then you have to remember it, that when object is placed behind 2F, image is smaller, inverted, real, and formed between F and 2F. What if object is placed at 2F? Light ray that goes parallel to the principal axis bends and passes through F on the other side. The light ray that goes through the optical center, it passes straight through. And when we put an object at 2F, exactly at 2F, we get an image exactly at 2F. This image is same in size as object. It is inverted, it is real. And you can check that out by performing this by yourself. You can make a lens, make these lines as they're supposed to be, and see if you get that right. Now, this, if we put an object between F and 2F, remember in the first diagram, we put object before 2F. Then in next diagram, we put object at 2F. Now we're putting between F and 2F. I hope you can guess what we will do next and then next. So if I'm putting an object between F and 2F, I pass this light ray which is parallel to the principal axis. It bends towards F. Then I pass a line through and through from optical center, which is straight through. I see an image, which is what? It is inverted, upside down, I mean. It is larger than the object, magnified, and it is also real. So if we put an object between F and 2F, we get an image which is bigger, inverted, real, and formed far behind 2F. And this is how a double convex lens is used in projectors for formation of images. Like this, in a projector, there is a screen inside that projector, which is very small screen, but with very intense light. Obviously, that source is definitely placed between F and 2F. So when light rays go through that lens, they form a very large image on the screen. Because this image is produced on a screen, that makes it obvious that this is a real image, larger and inverted. Any questions? Any query till now?
No, sir.
Good. So next what we do is we put object at F. When put object at F, the light ray that goes parallel to the principal axis is bending towards F. The light ray that is going straight through optical center is passing straight through, and the lines have become parallel to one another. When lines have become parallel to one another, that means that they will never meet, they will never intersect with one another. So if they don't intersect, they don't form an image. And if they don't form an image, we don't see an image. Okay, so it is also a case that if object is placed at F, no image is formed. Now, what do you think we are going to do next? We are now going to place an object between F and optical center. Remember, we started by putting an object behind 2F. Then we put an object at 2F. Then we put object between F and 2F. Then we put object on F. Now what we are going to do next? We are putting an object between F and O. If light ray goes parallel to the principal axis, it bends towards F. If light ray goes through O, the optical center, it passes straight through. The eye is positioned over here. And this is where the eye is important. I hope you can see that images images not formed because the light rays were spreading instead of merging towards one another. So they're spreading outward. So they will definitely not meet over here. So if we put an eye over there where they were supposed to meet, we can see that they are coming from a single point, and this is how we can see a very large image of the same thing. Okay, so this is what we see. We see image where the object is, that image is seen on the same side as the object is. What you can say about this image? Is this inverted? No, it is upright. So image is upright, image is bigger, and image is virtual. It is not a real image. It is a virtual image because we need to show an eye, and we cannot make this image on a screen. We can see it, but we cannot make it on a screen. This image is large, upright, virtual, and formed on the same side as the object is. And this is how a double convex lens is used as a magnifying glass. You know what magnifying glass is? You must have used it. A magnifying glass enables you to see something bigger. But to see that image, your eye has to be on a specific position. You can see it, but cannot produce this image on a screen. So when you're using a double convex lens as a magnifying glass, or magnifying glass simply, a magnifying glass is a double convex lens. So if you're using a magnifying glass, you're actually seeing a virtual large image. And to make that image, the position of the object that you're looking at has to be between F and O. Okay, if you have used a magnifying glass to see something magnified, you must have feel that difficulty over there, that you cannot just magnify anything. To magnify something, that thing has to be at a certain position. Then you can see the magnifying image. If your magnifier just moves a little bit here and there, you cannot see it. So that is how images are formed in double convex lens. And now we are done with light. All of it. Tomorrow we'll be starting from sound. And we will try to finish this whole chapter tomorrow so we can move to the next chapter.
So did we have a class yesterday?
No, we did not. I was not feeling good, so
Yes, sir.
I called it off. So see you people tomorrow.
Okay, sir. Allah Hafiz.
Allah Hafiz.